Nearly 4,000 species of snakes live on our planet today. These scaly, legless reptiles inhabit every continent besides Antarctica, adapting to an incredible range of climates and habitats, from tropical rainforests to sandy deserts. Snakes are some of the world's most colorful, innovative, and sometimes dangerous predators. But snake species weren't always as diverse and sophisticated as they are today. Long before there were giant pythons or venomous cobras, the ancestors of snakes were small, unremarkable lizards. These primitive creatures lived during the late Jurassic and early Cretaceous periods, roughly 160 to 100 million years ago. Back then, our planet was ruled by dinosaurs, the biggest terrestrial animals to ever walk on Earth. Dinosaur groups, like sauropods and ceratopsians, were growing larger than ever during the Cretaceous period. But in the shadows of these monsters, lesser-known reptile groups were undergoing transformations of their own. This is where the story of snake evolution really begins, with small populations of terrestrial lizards living in dense forests across the southern hemisphere. Within these lush ecosystems, lizards often maneuvered through tree roots and dense underbrush, where they hunted smaller forest dwellers like insects and worms. To help them squeeze through these confined spaces, some lizards evolved longer, sleeker body plans, and their legs gradually began to shrink. It's a common misconception that snakes suddenly lost all 4 of their limbs from neglect or disuse. Instead, this evolutionary process happened gradually, over millions of years, due to natural selection, unfolding in stages that we can actually identify within the fossil record. Most basal snakes lost their forelimbs long before their hind limbs. For example, Najash rionegrina was a 2-legged, terrestrial reptile, often considered a transitional species in the evolution of snakes. Najash's body was long and flexible, and its jaws opened wider than those of typical lizards, which allowed it to consume larger prey. However, its anatomy was more primitive, retaining its sacrum, pelvic girdle, and 2 small but functional hind legs. Even though Najash had legs, they were probably too small to be its primary way of moving around. Najash probably traversed the desert floor, not by walking, but by wiggling or undulating its body, an early example of slithering locomotion, which is common among snakes today. It may have then used its hind legs for more niche activities, such as burrowing or mating. Najash remains one of the most primitive snakes ever discovered, but it wasn't the only basal snake developing during the Cretaceous period. Another ancient species belonged to the genus Pochahochus, which dates back to roughly 98 million years ago. Fossils of Pochahochus were first discovered among marine limestone, suggesting that it lived at least part of its life underwater. Like Najash, Pochahochus was a transitional species, possessing some lizard-like characteristics, including a pair of hind limbs. However, in the case of Pochahochus, the limbs were less functional. Over millions of years, the hind limbs of basal snakes would become smaller and vestigial. But in some cases, they didn't disappear entirely. In fact, evidence of these vestigial hind limbs can still be found in modern boas and pythons, which retain internal remnants of pelvic bones, along with small external spurs near the back of their body. These little structures may not look like much, but these spurs help us understand how snake anatomy evolved over time. By the end of the Cretaceous period, snakes were becoming more advanced in carving niches as potent prehistoric hunters. But the world was soon rocked by a devastating extinction event, known as the Cretaceous phylogeny, or KP. In this new era, these formidable hunters mostly lived in vast, tropical ecosystems that were slowly expanding across the Earth. During the Paleocene epoch, the climate was generally hot and humid, so tropical biomes like rainforests became lush epicenters of prehistoric life. All kinds of mammals, reptiles, birds, and fish lived in these prehistoric jungles, providing abundant food for larger snake species, including a fearsome predator known as Titanoboa sarajomensis. This humongous semi-aquatic monster grew an estimated 13 meters long, making it the longest snake species ever discovered. Titanoboa shared many physical characteristics with modern-day boas, but fossil evidence suggests it may have behaved more like an anaconda. When hunting, Titanoboa likely immersed itself in shallow, swampy water. This natural camouflage allowed Titanoboa to disguise its massive body and stealthily ambush its prey. First, it bit down with hooked teeth before using its long, muscular frame to squeeze the life out of its prey's body, a typical hunting behavior among some modern snakes. Known as constriction, Earth stayed warm and tropical during the Paleocene and early Eocene, until it began a long and gradual cooling pattern around 50 million years ago. As temperatures slowly declined, the forests that covered much of the planet started to shrink, giving way to more open habitats like woodlands, grasslands, and savannas. As Earth's ecosystems became more diverse and distinct during this period, snakes adapted to different niches, leading to a wider variety of physical traits and behaviors. Consider the challenges of hunting in open ecosystems like grasslands. These spacious biomes offer fewer natural obstacles for snakes to hide behind, making it more difficult to surprise or ambush their targets. Prey animals in these open ecosystems also tended to be faster, so snakes had to evolve new ways of claiming their kills. The ancestors of vipers and elapids, for example, evolved fast-acting venoms that were strong enough to immobilize and kill animals, often larger than themselves. Delivering this venom through their fangs, they attacked, not by slowly constricting their bodies, but by lashing out with rapid strikes, sometimes killing their targets in a matter of just minutes. Some species also developed finely tuned sensory organs to help them hunt across a wider range of ecosystems. Pit vipers, for example, developed special organs close to their nostrils that allow them to sense infrared thermal radiation. With these so-called pit organs, vipers could hunt in the dead of night by tracking the body heat of warm-blooded prey. It's unclear when exactly snakes developed perhaps their most iconic sensory organ, their forked tongues. Forked tongues are not unique to snakes. They're somewhat common among squamate reptiles, like monitor lizards and some skinks, but that doesn't make these perceptive organs any less fascinating. Unlike most other animals, snakes do not use their tongues to taste their food. Instead, these specialized appendages are used to collect chemical particles from the air or ground. Those particles are then brought back into their mouths, where they're analyzed by a chemoreceptive structure known as the Jacobson's organ. This organ provides sensory information so that snakes can interpret their surroundings, locate mates, and even track prey animals, sort of like a chemical navigation system. With these advancements in perception, anatomy, and behavior, snakes had evolved many spectacular and modern features by the Miocene epoch, which began about 23 million years ago. During the late Miocene and then Pliocene, which ended 2.6 million years ago, Earth's climate continued to get colder and drier, further expanding open habitats where venomous species thrived. Some resilient groups, like cobras and vipers, even adapted to life in the driest parts of the world. The ground in these areas was often loose and sandy, so snakes developed a new kind of locomotion, called sidewinding, to help them cross deserts and scale sandy slopes. Around this time, sophisticated snake species were plentiful, but before they could reach the modern era, these snakes had to overcome some extremely cold conditions. We're talking, of course, about the Pleistocene epoch, a time of repeated ice ages that shifted global temperatures and radically altered our planet's ecosystems. During the Pleistocene, much of the northern hemisphere was covered by icy tundra and grassy steppes, where temperatures were often too cold for snakes to comfortably survive. Many snakes could only live in warmer regions, closer to the equator, while other species in more temperate areas found unique ways of braving the long, cold nights. Like mammals hibernating during the winter, snakes may enter a state of seasonal dormancy, called brumation. During brumation, they dramatically reduce their breathing and metabolic rates, allowing them to conserve energy. Thanks to adaptations like brumation, many snakes survived the Pleistocene's glacial periods. Another extinction event would rock the world's ecosystems at the end of this period, leading to the loss of many large mammals, like direwolves and saber-toothed cats. However, snakes remained successful predators into the modern era. Unfortunately, human activity has dramatically reduced and fragmented snake habitats around the world, particularly in regions like Southeast Asia and South America. We've also introduced invasive animals into their environments that either steal their prey or hunt snakes directly, such as mongooses. Despite these challenges, snakes have found ways to coexist with humanity. They live in our parks, gardens, and suburbs, feeding on common pests and slithering through the forgotten corners of our lives. While snakes can occasionally be scary, they are remarkable creatures with an extraordinary past.